It's a cold, moonless night, the kind that feels suspended outside of time, where the air itself forgets how to move. You're walking alone, the streetlights bleeding into fog, when it happens too fast to stop. Headlights, screeching tires. Your heart seizes. You see it too late. But before the impact, something impossible occurs. An elderly stranger appears out of nowhere, grabbing you, hurling you to safety, and taking the blow meant for you. In the silence that follows, you see their body crumpled in the road, still, lifeless. Later, a police officer hands you an envelope found in the stranger's pocket. It's addressed to you. Inside, just 2 words: study physics. You don't know who they were or why they gave their life for yours, but something about it haunts you. A command written in ink and blood, a riddle with no context, and so you obey. It becomes your compass. You dedicate your life to the pursuit of physics, driven by a mystery stitched into your survival. Years pass. You rise in the field. Awards, discoveries, theories turned reality, until one day, it happens. You build it, a time machine, and as you stare at the humming machine before you, buzzing, glowing, real, the final puzzle piece slides into place. You know what you have to do. You open the frame on your wall, remove the letter you've carried for decades, and tuck it back into its envelope. You step into the machine. You enter the coordinates, the night of the accident, the night everything began. The fog still hangs thick. You arrive seconds before the car. You see your younger self. You run. You shove them to safety. And just like that, you D. But now, everything falls apart. Because who wrote the letter? You didn't create it, you were given it. But now, you're the one giving it. The paper never had a beginning. It loops, endlessly passed from one version of you to the next, cycling through time like a ghost. This is the Bootstrap Paradox, a causal loop where an object or piece of information exists without ever being created, passed from the future to the past, and back again. It's not just science fiction. It's a logic bomb placed at the center of time itself. Where did the letter come from? Who was its author? No one, and everyone, because the loop doesn't start, it sustains. Like a snake eating its own tail, the event is both the cause and the effect. The past gives birth to the future, and the future resurrects the past. And here's the part that makes physicists lose sleep. It's logically consistent. It breaks no known laws of physics. The equations of general relativity, Einstein's masterpiece, allow for such loops. In theory, at least, the universe does not forbid this closed circle of cause and effect. The paradox is not one of logic, but of meaning. Because if the letter has no origin, if the idea to study physics didn't come from you, but from a version of you shaped by the letter, then where did the idea come from? Nowhere. It simply exists. A thought with no thinker, a message with no messenger, a destiny with no decision. And if that's possible, what else is? This is where time travel begins to shred not just science but identity. If you're caught in this loop, do you still have free will? Or is your entire life the echo of a choice that was never made? You didn't choose to become a physicist. You had to, because the man in the road you already did. You're no longer a person walking through time. You're a knot woven into it. The Bootstrap Paradox doesn't just break the arrow of time. It breaks the arrow of self. And we're just getting started, because buried inside this riddle are even deeper paradoxes of fate, decay, identity, and the boundaries of existence itself. The kind of questions that drag science into the realm of philosophy and leave both trembling. So let's dive deeper. If the universe permits such loop, then what happens when we keep repeating them? What happens when the loop loops? Time travel doesn't unravel the universe in one clean tear. It shreds it strand by strand. Because once you accept the Bootstrap Paradox, the floodgates open, and what spills out isn't just one contradiction, but a storm of them, each more disturbing than the last. Let's return to the loop. You, the older you travel back in time to save your younger self. You hand over the letter. The teenager becomes the physicist. The physicist builds the machine. The machine births the moment. The cycle is complete. But now ask yourself, does the loop age? Each time the envelope passes from one version of you to the next, the paper fades, the ink bleeds, the folds deepen. Over countless iterations, the letter becomes brittle, a relic worn down by time, even as it cycles through it. This is the restoration paradox, a contradiction hiding in plain sight. If the object exists in an eternal loop but still experiences decay, then eventually it fails, it burns, it rips, the message fades, the loop breaks. And if the loop breaks, if just one copy of you fails to deliver the letter, the entire chain collapses. You never study physics, you never build the machine, you never travel back, you die. But if you die, no one travels back to deliver the letter in the first place. This isn't just a paradox, it's an existential razor, a contradiction so sharp it could slice reality into pieces. So which is it? Does the loop sustain itself forever, impossibly immune to entropy? Or does it collapse, doomed by the very physics it depends on? Either answer fractures something fundamental, and still, the paradoxes go deeper. Let's rewind again. You only chose to study physics because the letter told you to, but that choice was never yours. The idea didn't come from within, it was handed to you, and it only exists because you eventually hand it to yourself. That's the ex nihilo paradox, a thought born from nothing, a command without a commander, a future pulling the past into its orbit, retroactively assigning meaning. And this raises a devastating possibility. What if you never had free will at all? What if your whole life, your studies, your invention, your sacrifice, were never choices, but inevitabilities, predetermined roles in a cosmic script written by a version of you that you can never disobey? You were always going to build the machine. You were always going to die in the fog. You were always going to become the ghost that saves yourself. There was no fork in the road, just a single rail and you bolted to it. This is the predestination paradox, and it slices directly into our most sacred illusion, that we choose our path, that we shape our destiny. But here, in the looping corridors of time, choice becomes a shadow, and shadows can't steer the light. Still not uncomfortable enough? Let's make it worse. What if, at the very last second, you decided to do nothing? You travel back to the moment, you see your younger self, you remember what's supposed to happen, but this time, you hesitate, you freeze, you let the car hit them, they die, which means you never grow up, you never build the machine, you never go back. But if you never go back, who let the younger you die? No one, but they did die. But they didn't, because if they had, you wouldn't be here. This is the auto-infanticide paradox, the most disturbing of all. It tells us something bone deep about the logic of time. You can't kill your younger self, even by doing nothing, because if you do, the conditions for your presence in the past vanish. Your existence retroactively erases itself, and yet, somehow, you're still standing there. The universe, it seems, won't allow it, not by principle, but by pure mathematical contradiction. In some sense, this makes the past indestructible, not because it's sacred, but because breaking it breaks the entire mechanism of time travel. And here, we meet the true monster, hiding in the fog, causal consistency. The idea that no matter what you do, events must unfold in a way that's logically self-sustaining. If you go back, your actions are part of the past, not new branches, but already woven threads. You were always in the story, whether you knew it or not. In this worldview, the universe is a book. You can read any page, in any order, but you can't rewrite the chapters. Even if you try to shoot your younger self, the gun jams. Try to burn the letter, the wind catches it, and you fumble. Try to run away, the car swerves, hits you anyway. No matter the move, the loop defends itself. And so, the question deepens. If you can't alter the past, if you're just another line in a self-consistent story, then, are you even real? Or are you just a reflection bouncing endlessly between mirrors? A ripple repeating itself in the same pond. A consciousness trapped not in time, but in narrative. And yet here's the strangest part. Some physicists accept all of this. not as metaphor, not as fiction, but as mathematical possibility. Einstein's equations, when extended into curved spacetimes, allow for closed time-like curves loops in time where cause and effect fold into themselves. Reality, as far as the math is concerned, permits a story like yours, one where a person saves themselves, loops endlessly, and lives not on a straight line, but a circle. And yet no experiment has ever confirmed it. It's theoretical, terrifying, and intoxicating, because if one loop is possible, then so are 1,000, each a corridor in the labyrinth of time, each rewriting what we thought we knew about destiny, identity, and choice. And this pile-up of paradoxes isn't even the edge of the rabbit hole. It's just the welcome mat, because the moment we accept that the future can reach into the past, we must ask, what is the past really? Is it dead? Or is it still there, waiting, watching, and possibly changeable? But how, and with what rules? Let's find out. What if the past never actually disappeared? What if it's not gone, not vanished like smoke, but still there, behind a veil of perception, as real as this moment, as solid as your breath? What if tomorrow already exists, too, waiting just beyond the bend? Imagine time not as a line, but as a river. You are a canoe, floating on the current. The water carries you forward, effortlessly, silently. You don't need to row. You can't turn back. And yet, the parts of the river you've already passed still exist, still ripple, still swirl. They didn't vanish when you moved forward. They're simply behind you now, upstream, out of sight, but still part of the river. Jack Finney, a master of time travel fiction, once wrote that we aren't bound to time, we're merely carried by it, ferried, like leaves on a current, and for all our effort, we don't steer. But what if that's not just metaphor? What if that's reality? Because this poetic river is exactly how many physicists now describe time, not as a fleeting illusion, but as a landscape, already there, already drawn, from its turbulent source in the Big Bang to its final plunge into cosmic darkness. Every moment that's ever happened, every moment that will, already exists. This idea is called eternalism, and it breaks everything you thought you knew about time. Eternalism says the past is not dead, the future is not unborn, time is not a candle burning itself away. Instead, the entire structure of time exists all at once, a four-dimensional block, a cosmic sculpture. You don't move through it like a train on a track. You are already threaded through it from start to finish, like a bead on a wire that runs through eternity. Your birth, your heartbreaks, your last breath, they're all there, always have been. And this isn't just philosophical poetry, it's backed by science. Because if time is an illusion, it's a very consistent one. In fact, physics real, hard physics requires that we treat time as a dimension, not a flow, not a ticking clock, but a coordinate. Just like north, or west, or up, if you can be here in space, you can be now in time. But just like here means nothing without a map, now means nothing without the whole of space-time. And once you accept that, you realize something else. There is no universal now. There is no, this is the present, stamped across the universe. This is what Einstein gave us in 1905 with his Special Theory of Relativity. The idea that time is relative, that what's now for you might already be tomorrow for someone else or yesterday. Two people moving at different speeds or under different gravitational forces will disagree about what events happen simultaneously, and neither is wrong. This means time isn't just a slippery illusion, it's a fractured, personal experience. Every observer walks through their own version of now, and so the very idea of a single, objective present collapses. If there is no singular present, then how can the past be gone? How can the future not yet exist? You can't delete what's real for someone else. And so, reluctantly, beautifully, we are led back to eternalism. Time is a block, a vast four-dimensional slab of reality. Past, present, future, all laid out, all real, all untouchable. To walk you through this block universe, Imagine standing outside of time itself, floating, godlike, beyond the veil. You look down and see your entire life all at once. The child, the adult, the elder. Every version of you, every decision, every heartbreak, every joy, all happening, all there, all now. Einstein hinted at this when he wrote, "The distinction between past, present, and future is only a stubbornly persistent illusion. The illusion is survival. The illusion is change. The illusion is time itself." But if time is already mapped out like ink on a cosmic scroll, what does that mean for you? Are you just a puppet moving through a script? Are you a character reading one sentence at a time from a story that's already written? Or is awareness something more, a light moving across the page, illuminating each moment one at a time? If the past still exists, could we visit it? If the future is real, could we peek ahead? And if we could, what would we change? Or would we, like all great characters, discover that what's written is already so, that we were always going to be here, that our choices are already etched into the marble? This is the tension eternalism creates. It gives us a universe filled with every version of us, every joy, every mistake already real, already waiting. It gives us a multiverse of moments, not scattered across parallel dimensions, but stacked like pages in a journal already written. And yet we still feel like we're choosing. We still weep at the turning points. We still breathe in the unknown. We still hope. Maybe that's what makes us human in a block universe. Not that we're free, but that we feel as if we are. And if eternalism is true, then death isn't an end. It's a page, still there, still retrievable, still you. Your laughter in childhood, still echoing upstream. Your great-great-grandchildren, already dancing downstream. The river never forgets. It only flows through our awareness. And that awareness, this now, is nothing but a flashlight moving across the canvas. The painting is finished, but we still feel each brushstroke as it arrives. And so we ask, if the past exists, can we touch it? Can we stand in it? Can we build a machine, not to defy the river, but to turn upstream? To pedal against time? The science says, maybe. And if so, we must understand the true nature of what we're paddling through. Because it's not just time, it's space-time, a fabric, a field, a map with both roads and hours stitched into it. And to alter time, we must first learn how to bend the fabric itself, how to reshape space-time, just as gravity does, to open doors we thought forever locked. Let's step into that world. Let's meet the genius who saw the shape of time and taught the world how to fold it. What if time isn't something that passes, but something that is? Not a ticking metronome, counting down from birth to death. Not a flowing river, but a frozen landscape, a vast four-dimensional sculpture where every moment has already found its place. This is the idea at the heart of Einstein's legacy. This is the block universe. And it didn't start as poetry, it started with math. In 1905, a 6-year-old patent clerk named Albert Einstein published a paper that would set fire to the foundations of physics. He called it the Special Theory of Relativity, and in it he dismantled one of the most sacred assumptions of science, that time is absolute. Before Einstein, the universe was thought to run like a cosmic clock. Time ticked evenly for everyone, everywhere, a universal heartbeat that synchronized all events across space. But Einstein said no, there is no master clock. There is no universal now. Time is relative. It bends, it shifts, it flows differently, depending on who you are and how fast you're moving. Imagine two observers watching the same two events, a lightning strike in the east and another in the west. One observer is standing still, the other is running. According to Einstein, they may disagree about which lightning bolt struck first. And here's the catch. They're both right. There is no absolute sequence. Time is no longer the same for all. It becomes local, personal, subjective. One person's past could be another's future. And if time can't agree on the order of events, how can it be passing for everyone in the same way? It can't, which leads to a radical realization. If events don't have a universal sequence, then they must all exist at once. Enter the block universe, a concept born not from fiction, but from the cold logic of relativity. Physicists began to imagine time not as a moving present, but as a dimension just like length, width, and height. Instead of the universe being three-dimensional, it is four, the three dimensions of space plus time. Together, they form a single fabric, space-time. In 1908, Einstein's former teacher-mathematician Hermann Minkowski took this idea further. He said, "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." This wasn't metaphor, it was physics, and it changed everything. In a block universe made of space-time, all events past, present, and future coexist. They don't happen so much as exist. The world is no longer a story unfolding in time, but a story laid out across it. Your birth is a location. Your death is a location. They are not unfolding, they are already there. You are a line threaded through the block, a world line, as physicists call it. To visualize it, picture the dot that represents you. Not a snapshot, but a dot that moves with every tick of your personal clock. As time advances, your dot draws a line mapping your motion through the block universe. Everything that exists can be traced in this way. A planet's orbit, a loop, a photon's journey, a diagonal streak at light speed. Your own life, a beautifully tangled thread woven with those around you. Now join the dots of your past and future. You get a curve, a path through the fabric of reality. You can't leap off that path. You can't bend it. It is your fate, stitched into space-time. And yet here you are, conscious, choosing, feeling free. This is the magic of the block universe. It gives us a deterministic cosmos, and yet we feel like authors within it. But how do we know this is more than elegant theory? Enter general relativity. 10 years after special relativity, Einstein delivered its more ambitious sibling, the general theory of relativity. While special relativity dealt with speed and simultaneity, general relativity deals with gravity. And here's where space-time becomes something more than a coordinate grid. Einstein proposed that gravity is not a force, not a pull like Newton imagined, but the curvature of space-time. Massive objects warp the fabric. They create indentations, wells, hills, and valleys in the invisible terrain of reality. To demonstrate it, imagine a trampoline. You place a heavy ball in the center, it sags. Now roll a smaller ball around it. It curves inward not because of a force, but because of the shape of the surface beneath it. That's gravity, according to Einstein. The Earth orbits the Sun not because it's pulled, but because it's following the curve of space-time shaped by the Sun's mass. This insight was so revolutionary that when it was confirmed during a solar eclipse in 1919, when starlight was observed bending around the Sun, Einstein became an overnight global icon. The theory didn't just work, it predicted things Newton could not explain. Take Mercury's orbit. For years, astronomers noticed something strange. Mercury's path around the Sun wasn't quite right. It shifted precessed in a way Newton's equations couldn't fully account for. Einstein's equations solved it perfectly. Why? Because Mercury orbits close to the Sun, deep within its gravitational well. The curvature of space-time is stronger there, more pronounced, and only general relativity could explain the subtle warping that caused Mercury's orbit to twist. This was the beginning of proof, and it only got stronger. Black holes, gravitational lensing, time dilation, gravitational waves. Again and again, the predictions of curved space-time matched observation, not just metaphorically, but measurably. So when we say, the block universe is real, it's not a thought experiment. It's a scientific model backed by equations that have passed every test thrown at them. And yet, we live as if time moves. We wake, we work, we age. We dream of the future and long for the past. We feel the pull of now. So what is that? Some physicists call it the illusion of consciousness, the moving spotlight of awareness scanning across the block. Our minds create the feeling of now as they process one slice at a time. Others suggest we misunderstand what change even island, that nothing actually becomes it just island. But no matter how we slice it, time, as we experience it, is not the time of the equations. It's personal, fragile, and deeply entangled with meaning. Because if your world line is fixed, if your life, every heartbreak, every triumph is already there, then your presence becomes the only mystery left. Why this moment? Why now? And perhaps more importantly, can we ever step outside the block? Can we twist its fabric, bend it, travel through it like space? The math says yes, in theory. The universe may be a sculpture, but maybe, just maybe, we've found the chisel. Let's look deeper into the experiments that reveal the cracks in time. Sometimes the universe doesn't whisper its secrets. Sometimes it carves them in the sky for those with eyes to see. For centuries, humanity trusted Isaac Newton's grand vision, a universe governed by gravity, a force pulling objects toward each other across the void. It worked. It launched cannonballs, mapped planets, and built the mechanical heavens. But not all was well in the clockwork cosmos. One planet, the smallest and swiftest, refused to play by the rules: Mercury. Orbiting close to the Sun, Mercury danced in a way Newton's equations couldn't quite explain. Its path didn't loop perfectly. It precessed the closest point in its orbit, the perihelion, shifted with every revolution, just a fraction, a whisper. But over time, it became undeniable. Astronomers calculated, recalculated, invented hypothetical planets. Vulcan, they called it, lurking unseen, tugging Mercury off course. But Vulcan never appeared, and Newton's perfect clock started to crack. It wasn't until 1915, when a now world-famous Albert Einstein sat down with a blank page, that the truth came into focus. His weapon? Not a telescope, not a spaceship, a pencil, and a new theory of reality, general relativity. Instead of imagining space as an empty arena and gravity as a force acting across it, Einstein proposed something far stranger and far more beautiful. Gravity is geometry. Massive objects, stars, planets, even you warp the fabric of spacetime. The greater the mass, the deeper the well. Time slows, light bends, and the paths of orbiting objects are not pulled, they are simply falling through curves. Imagine again a trampoline stretched tight. Place a bowling ball in the center, the surface dips. Now roll a marble near the edge. It circles inward, spiraling along the curves carved by the heavier mass. That's not a force, that's motion through curvature. Mercury's orbit wasn't disobedient. It was moving exactly as it should, not through flat space, but across a curved space-time deeper than Newton ever imagined. Einstein did the math, and when he added the curvature near the Sun to Mercury's predicted path, the numbers matched reality perfectly. He had cracked the orbit no one else could, not through guesswork, through geometry. It was the first major victory of general relativity, but it would not be the last, because Mercury was just a clue, a riddle from the solar system's inner edge. What Einstein unlocked was far greater: the ability to predict how space-time behaves everywhere, from stars to galaxies to the deepest voids. And the deeper we looked, the more we found. During the 1919 solar eclipse, light from distant stars bent around the Sun's silhouette, confirming Einstein's prediction. Decades later, scientists detected gravitational lensing entire galaxies, bending light like a glass bowl, warping the sky behind it. Still later, we caught gravitational waves, ripples in spacetime caused by colliding black holes, ringing out across the cosmos like the aftershock of a bell struck in the dark. Every experiment confirmed what Einstein whispered: space and time are not separate. They are one, and they bend. But what bends can break. What curves can twist. And what follows those curves can fall into places we've never imagined. Let's return to that trampoline. This time, drop something heavier. Not a bowling ball, but a mountain, a star. The dip becomes a crater, deeper, steeper. Now drop something infinitely dense, a collapsed star, crushed by its own gravity. The dip becomes a hole, no bottom, no escape. This is a black hole, the place where space-time folds in on itself, where gravity becomes so intense that even light cannot flee, where time begins to behave strangely. Near a black hole, clocks tick slower, much slower. An observer falling toward the event horizon might feel seconds pass, while a friend watching from a distance would see centuries unfold. This isn't science fiction. It's been measured. In 1976, a pair of astronomers sent atomic clocks aboard aircraft flying around the Earth and found they ticked slightly slower than identical clocks on the ground. More recently, in 2022, physicists measured time moving differently between two atomic clocks placed just 1 millimeter apart because of a tiny difference in gravitational strength. This is the everyday evidence of Einstein's truth. Time is not fixed. It is elastic, mutable, woven into the shape of space itself. The deeper you are inside a gravity well, the slower time moves. And that brings us to a profound possibility. Can we use gravity to travel through time? Because if time slows near mass, then standing near something massive enough like a black hole could let you jump into the future. You wait minutes. The universe waits years. The closer you are to the singularity, the deeper the well. And the deeper the well, the slower your time ticks. Theoretically, you could orbit the event horizon for a few hours and return to find 100 years have passed. You wouldn't feel the passage, but your world would be gone. This was the core concept in Interstellar, the 2014 film crafted with help from physicist Kip Thorne. It wasn't fantasy, it was relativity, dramatized. In that world, 1 hour near a black hole equaled 7 years on Earth. The science held, we already see time dilation in orbit. We already use relativistic corrections for GPS satellites. Without adjusting for general relativity, your phone's navigation would drift by kilometers each day. Our technology works because time is curved. And that means time isn't just a story we tell. It's a terrain we walk. It bends, it twists, it loops. And if we learn to map its curves to ride its warps and wells, we may not just understand time, we may learn to navigate it. Time travel isn't just a fantasy anymore. It's a question of engineering. And the path forward starts with a deeper truth. That time is a dimension, and we are travelers already. So what happens when you push that travel to the edge? When you don't just flow forward but leap ahead? Let's ride with the particles that already do it. Let's chase the cosmic messengers that travel at the speed of near eternity, and learn how they prove conclusively that time travel to the future is real. You are not a traveler moving through time. You are a shape in time, a path, a ripple, a line drawn through the invisible fabric of space-time, curved, looping, tangled with others yet unmistakably yours. This is your world line. In the physics of the block universe, everything that exists traces a line through space-time. Every particle, every planet, every thought and footstep. If space is the stage and time is the script, then your world line is your character moving frame by frame, already written, already there. Even if you never move a muscle, you still have a world line. Because time is a dimension, and simply existing means you're drifting through it, like a bead sliding along a string, like a comet carving its arc across the stars. The future, already mapped. The past, still printed behind you, and the present, just the point where your awareness glides along the line. It's strange, isn't it? To think that your entire life, every version of you exists as a continuous four-dimensional shape, a knot tied into the very geometry of the cosmos. But this isn't speculation, it's science. And if we follow the threads of that science far enough, we land on a question far more shocking than, is time travel possible? The question becomes, are we already doing it? Because in a very real, measurable, testable way, we are. Let's rewind to 1930 seconds Italy. A young physicist named Bruno Rossi was obsessed with a strange phenomenon, mysterious particles called muons, born in the upper atmosphere when cosmic rays from distant galaxies collide with Earth's air. Muons are unstable. They decay in a flash. Their half-life is 1.56 millionths of a second. By all calculations, they shouldn't survive long enough to reach the ground. They should vanish in the sky, like snowflakes above the clouds. But Rossi noticed something odd. They were making it. Far more muons were reaching Earth than the numbers allowed. It didn't make sense unless time itself was acting differently. So, Rossi designed a bold experiment. He loaded detection equipment onto an old bus and drove up the winding roads to Echo Lake high in the Colorado Rockies, 2 kilometers above sea level. There, he measured the muons at high altitude, then compared the results to the number arriving down below. And the answer was clear. The muons were experiencing less time. Because they were moving so fast near the speed of light, relativity was in full effect. For them, only a fraction of a second passed. For us, many seconds ticked by. To the muons, the Earth's surface wasn't far away at all. From their perspective, they hadn't yet had time to decay. They had time traveled into our future. This is called relativistic time dilation, and it's not theoretical. It's been proven, repeated, and measured from particle physics to spaceflight. It tells us something staggering. Speed warps time, and if you move fast enough, really fast, close to the speed of light, you can leap through time itself. Let's say you became the muon. Strap into a spacecraft, blast off at 99.99% the speed of light, travel around the galaxy, return. For you, 5 years pass. Back on Earth, 500 years. You've moved through space, but you've skipped through time. You've drawn your world line across a deeper curve in space-time, stretching forward, pulling your presence into a future far beyond your birth. This is not science fiction. This is physics, and it means that time travel into the future is not only possible, it's already happening. Every satellite, every astronaut, every high-speed particle is a time traveler just by being in motion. Even the GPS in your phone depends on this. The satellites orbiting Earth experience time differently. Their clocks tick faster than ours due to weaker gravity and constant speed. If we didn't account for this, your location would be off by miles. And so, in every moment, your phone is correcting for time distortion, adjusting the math because time is not constant. And if time isn't constant, what is? Only one thing: the world line, your shape in space-time, the record of your being, the trail of your becoming. Imagine tracing every moment of your life, every breath, step, blink into a glowing thread of light. It curls, it spirals, it intersects with others. Some threads drift away, others coil tighter. Now zoom out. You see billions, trillions. The galaxy becomes a tapestry of world lines, each one a life, a story, a destiny stitched into space-time like thread into cloth. And where do they go? Some end early, some stretch impossibly far, some loop haunting themselves across time. Because if motion can stretch time, then the right motion, the right warping of space-time, might allow you to bend your world line back, not just forward into the future, but around into the past. A closed world line, a closed time-like curve. And in that curve, if physics allows it, you might intersect yourself, not just metaphorically, literally. That's the goal of every time machine, not to leap off the line, but to fold it, to bend the path so it touches itself, to become your own past or your own salvation. But doing so isn't just a technical challenge, it's a philosophical earthquake, because once your world line is closed, you're no longer a traveler in time. You are a loop, a cycle, a story with no beginning. And the Bootstrap Paradox returns. Did you build the machine? Or did the machine build you? Where did the idea begin? In a closed world line, beginnings evaporate. Causality becomes a Mobius strip, endless, twisted, complete. And you? You're the knot, tied in the dark fabric of space-time. Self-made, self-contained, self-forged. Your memories are echoes. Your future is déjà vu. Your death is your birth, and your birth is your legacy. So when we ask, can we time travel? What we're really asking is, can we step off the line? Can we untie the knot? Or are we forever tangled into the shape of the cosmos itself? Let's push further, because while speed can bend time forward, there are other ways to bend the line even more. What happens when we throw gravity into the mix? What happens when we fly too close to the edge of a star or a black hole? Let's find out. Not all time travelers ride starships. Some are born in violence, invisible, microscopic, ancient, born from the chaos of exploding stars and flung across the cosmos like bullets from the barrel of creation. They're called muons, unstable particles, cousins of electrons, created high in Earth's atmosphere when cosmic rays strike. Every second, millions of them rain down upon you. You don't feel it, you don't see it, but your body, your skin, your DNA is a landing pad for messages from other galaxies. But here's where the story breaks the laws of classical physics. Muons decay quickly. Their half-life is just 1.56 microseconds less than a millionth of a second. By that logic, they shouldn't make it from the upper atmosphere to the surface. They're born too high, too fast. It's like lighting a match at the top of Mount Everest and expecting it to stay lit all the way to sea level. Yet, they make it far more than predicted. They survive the journey, and for decades, no one could explain how, until one physicist, Bruno Rossi, drove a bus into the sky. It was 1,940 seconds America. Rossi packed his equipment and climbed into the Rocky Mountains to a place called Echo Lake, perched nearly 3,200 meters above sea level. He measured the muons there, then he measured them again, farther down at Denver, and again on the plains. Each time, the data told the same story. Muons were living longer than they should. At first glance, it seemed like magic or a mistake, but Rossi understood what was really happening. Time was stretching. Because muons move at nearly the speed of light, the rules of Einstein's special relativity take over. In their frame of reference, time is different, slower. The faster you move through space, the less you move through time. It's as if the muons are borrowing from the future to survive the present. To them, the journey to Earth's surface is short. They haven't lived long enough to decay. To us, watching from the slower rhythm of earthbound time, they should be dead. But they're not. This isn't a theory. This is measured reality. Time dilates, expands for objects in motion, and that changes everything, because it proves in real, testable terms that time travel into the future is already happening. Not in some distant sci-fi fantasy, but here, now, with every cosmic storm that slams into our atmosphere. The muons are moving forward in time faster than we are. And if they can, so can we. Imagine this. You become the muon. You board a spaceship. You accelerate to 98% the speed of light. You loop the galaxy. From your perspective, only a few years pass. But back home, a century has gone by. You return to a planet that has forgotten you, a civilization you barely recognize, a future you skipped to simply by riding a deeper curve through space-time. It's not science fiction. It's physics. It's already in motion, all around us in satellites, in CERN's particle colliders, in muons falling from the sky like cosmic snow. And if we stretch this further, we find the story isn't just about muons and motion. It's about the budget of existence. According to Einstein, anything moving through space-time has a limited budget, a finite amount of movement. And if you spend more of that movement on space, you must spend less on time. That's the space-time trade-off. So if you move extremely fast, close to the speed of light, your time slows down, relative to someone standing still. The muons spend almost everything on speed, so they spend almost nothing on time. They survive, they stretch, they fall into the future. Now imagine we harness that. Not with particles, but with people. Time travel becomes not a leap, but a stretch. You stretch your experience through space. You contract it in time. The result? You skip forward, and the faster you go, the more dramatic the jump. But there's a catch, a heavy one. Speed requires energy, and energy has mass. Einstein's famous equation E equals mc squared tells us that the more energy you pump into a traveler, the heavier they become. A person traveling at 99.999% the speed of light would weigh as much as a rhinoceros, and to accelerate them to that speed would require more energy than humanity uses in months. Time travel to the future is real but not easy. We already use it, unintentionally, in our technology. Every GPS satellite orbits fast enough and far enough from Earth's gravity that its onboard clock ticks differently than ours. Without correcting for relativistic time dilation, GPS would be useless within hours. Your phone's map would be off by miles. So we correct it, every second, every satellite, every signal, because the world we built assumes Newton's time. But the universe moves, according to Einstein's. And so, we stand at the edge of the possible. We know how to time travel to the future. We've done it with muons. We've done it with twins like Mark and Scott Kelly, NASA astronauts born just 6 minutes apart. But Scott spent 520 days in space, orbiting faster, deeper into the relativistic realm. When he returned, Mark was 6 minutes and 5 milliseconds older. It's tiny, but it's real. Scott skipped forward ever so slightly, like the muons, like the satellites, like every particle that dares to move fast enough through the fabric of time. These aren't stories, they're measurements, and they whisper to us, time is not what you think it, island. You don't live inside a clock. You live inside a field curved, flexible, governed by speed and gravity, a place where motion sculpts time, where the future can be touched, if you're willing to pay the price. And as we inch closer to that threshold, faster ships, stronger fields, deeper understanding, we must ask, is this the beginning of temporal navigation? Are we the first generation not just to understand time, but to shape it? The answer lies, not just in speed, but in gravity itself, because just as motion can slow time, so can mass, so can depth. What if we didn't have to go fast to travel forward? What if we just had to go deep, into the wells of gravity, into the jaws of black holes? Because down there, time ticks differently. And if we're brave enough to enter, we might come out somewhere new. If speed lets you cheat time, gravity lets you break it, not in defiance, but in obedience, because gravity, as Einstein revealed, is not a force pulling at you. It's the curvature of space-time itself. The deeper you fall into a gravitational well, the more time bends, stretches, slows, and in the deepest wells, time begins to tear. Let's start small. You're holding two identical clocks, not wristwatches, not gears and springs. These are light clocks, simple devices with two mirrors and a beam of light bouncing between them. Every tick is one bounce. Now set both clocks running. Take one and place it deep inside a gravity well, perhaps in the mountains, or aboard the International Space Station, or in the heart of a neutron star's pull, and leave the other on Earth. Wait, then bring them back together and compare. They're no longer synchronized. The one in stronger gravity ticks slower. Time crawled for it, not because the clock was broken, but because the fabric of time around it had stretched. This isn't science fiction. This is experiment. In 2022, scientists placed two ultra-precise atomic clocks, just 1 millimeter apart, one slightly higher than the other. The results? They ticked at different rates. Even a tiny change in height, and thus gravitational pull, was enough to split their timelines. That's the reality we live in. We're already experiencing gravitational time dilation every second of every day. The top of your head ages just a little faster than your feet. You've been time traveling, vertically, your entire life. The effect is small, imperceptible, unless we magnify it. So let's go bigger. Let's go cosmic. Let's go to a black hole. These aren't just collapsed stars. They're punctures in the fabric of space-time, regions of such dense gravity that not even light can escape. And near their event horizons, time slows so dramatically that it almost stops. In the film Interstellar, a crew lands on a planet orbiting close to a supermassive black hole named Gargantua. On that world, time is distorted so severely that 1 hour on the surface equals 7 years back on Earth. It sounds like fiction, but the math checks out. Kip Thorne, the Nobel-winning physicist who advised on the film, confirmed it using Einstein's equations. Get close enough to a massive black hole, and you can surf the edge of time itself. Spend a day, come back to Earth. Decades may have passed, Not in theory, in reality. And here's the twist. Earth has its own gravity well too. When Bruno Rossi drove up Mount Evans in the 1940 seconds to study cosmic rays, he wasn't just changing elevation, he was climbing out of time. Even at a few thousand meters above sea level, his body aged ever so slightly faster than it did at the base of the mountain. It's microscopic, but it's measurable, and it proves the principle. The deeper into gravity you go, the slower your clock ticks. Now imagine weaponizing that effect. Not with tiny clocks or satellites, but with entire missions designed to dive into time and come back out the other side. To time travel not by acceleration, but by descent. All you need is a gravity well deep enough. A black hole. The challenge? Surviving the journey. Crossing the event horizon is a one-way trip unless the black hole is rotating. Then, according to some solutions of Einstein's field equations, it may allow passage through a ring singularity and possibly out the other side. Where? We don't know. Another universe? Another time? Maybe both. This isn't confirmed science. It's the bleeding edge of possibility, a place where equations permit strange things and where reality begins to tremble. But even without diving in, we could orbit near the edge. Time would slow. Future centuries would tick by outside, while minutes pass for you. A machine built to orbit a black hole might be humanity's first functional time vessel. It wouldn't take you to the past, but it would preserve you, advance you forward, make you a witness to centuries in a single lifetime. But here's the kicker. You're already using this. Right now, GPS satellites orbit far above the Earth, moving fast, high in the sky, where gravity is weaker. Their onboard clocks tick faster than ours. To keep your phone from navigating you into rivers and buildings, engineers have to correct for time dilation. This isn't theoretical, it's infrastructure. Relativity is baked into our everyday life, and the more we understand it, the more we can use it to explore, to navigate, to leap. But we're still missing something. We've talked about speed, we've talked about gravity, but what about the edge of time itself? What if there were a tunnel, not through space but through space-time? A shortcut not just between stars but between eras? Could we walk upstream through the river of time? Could we travel back? Because that is where the real paradoxes live. The grandfather paradox, the auto-infanticide paradox, the idea that changing the past could erase your future and yet you already exist. If the universe allows such loops, what's stopping us? And if it doesn't, why not? Let's move deeper now, beyond speed, beyond gravity, into the speculative frontier, where time might not just bend, but fold, and where wormholes, cosmic strings, and quantum entanglement offer whispers of backward travel. Let's go there. Let's chase the next great contradiction. Time is not a highway. It's a boundary, one we cannot cross, not forward without immense effort, not backward at all. And the reason? The speed of light. Einstein didn't just give us new clocks and curved space. He gave us a cosmic speed limit, a law etched into the bones of the universe. No signal, no particle, no piece of information can move faster than light. Approximately 299,792 kilometers per second. That's the barrier. But it's more than just fast. It defines what's possible. In the geometry of space-time, every event, every moment and place has its own light cone. Picture a cone extending upward into the future and downward into the past. The sides of that cone represent everything light could ever reach and everything that could ever reach you moving at or below light speed. Step outside the cone, you've left cause and effect behind. Inside the cone, logic, reason, physics. Outside the cone, paradox. That's why time travel to the past is considered impossible. Because to do it, you'd have to move faster than light. You'd have to break the cone. But here's the twist. Einstein's equations, the very ones that gave us the cones, don't always forbid their violation. In fact, under certain extreme conditions, they permit it. Let's return to 1937. A Dutch physicist named Willem Jacob van Stockum publishes an obscure paper. The title? the gravitational field of a distribution of particles rotating about an axis of symmetry. Not exactly headline material, but hidden in the math is something wild. Van Stockham showed that if you took a massive cylinder, infinitely long and spinning fast enough, you could twist spacetime into a loop. Not a metaphorical loop, a literal one, a closed time-like curve. This means your world line, your path through time, could double back and intersect itself. You could shake hands with your past, whisper into your own ear, rewrite your own story. And it didn't require breaking the light barrier, just tilting the light cone, twisting spacetime so tightly around a spinning mass that your future folds into your past. This idea was expanded later by Frank Tipler, who explored the effects of a spinning cylinder 10 times the mass of the Sunday. If you spiraled around it just right, fast enough, close enough, your light cone would slowly tip backward, until suddenly, yesterday is inside your cone. Suddenly, you can go home to the past. The only problem? The cylinder must be infinitely long, and it must rotate billions of times per minute. Good luck building that. So physicists looked elsewhere, and what they found were even stranger possibilities. Enter the wormhole, a term coined by John Wheeler and first made famous in science fiction by Carl Sagan. Wormholes are tunnels, shortcuts through space-time, not just across distance, but possibly across time. Imagine space-time as a sheet of paper, 2 stars or 2 errors marked on it. Normally, you'd travel across the page, taking thousands of years. But what if you folded the paper so the 2 marks touched? That fold is the wormhole, and if you could move through it, you'd emerge on the other side instantly. No need to go faster than light because you've bypassed the space between. Sagan wanted this idea for his novel Contact, so he called up his physicist friend Kip Thorne, who ran the math and said, yes, wormholes could exist, but there's a problem. Wormholes are unstable. They collapse under their own gravity. Any traveler would be crushed before even reaching the midpoint, unless you prop them open with something exotic, negative energy. In quantum physics, even empty space isn't truly empty. Particles pop in and out of existence, virtual flickers of matter and antimatter. This fluctuation allows for the temporary borrowing of energy, including negative amounts. If we could gather and stabilize enough negative energy, we might be able to hold a wormhole open and keep it traversable. Thorne showed that if one mouth of a wormhole was accelerated to near light speed, then brought back, it would experience less time due to relativistic effects. Now one mouth is in the future, and the other remains in the past. Step into the future N and emerge from the past, just like that time travel. And this time, it doesn't require a spinning star or an infinite cylinder. It only requires 2 things: a stable wormhole, a violation of everything we think we know about causality. But wait, there's more. In 1991, physicist J. Richard Gott explored the possibility of using cosmic strings, hypothetical defects in space-time left over from the early universe. These strings would be infinitely long, thinner than an atom, and incredibly dense. Gott found that if 2 such strings moved past each other at high speeds, their gravitational field could bend spacetime into a loop, allowing backward time travel along a specific path. Even quantum entanglement has been considered. 2 particles, linked across vast distances, react instantaneously. It seems as though information travels between them faster than light. Could this be a loophole? Not quite. Entanglement doesn't allow actual communication faster than light. It's a correlation, not a conduit. Still, the possibilities keep stacking. Again and again, the equations don't say no. They say, maybe, under the right conditions. So what stops us? Paradoxes. Because if we can visit the past, we might try to change it. Kill our grandfather, prevent our own birth, write a letter we never received. These contradictions threaten to unravel logic itself. But some physicists believe the universe protects itself, that time travel to the past may be allowed, but changing the past is not. Others believe in parallel timelines, that when you travel to the past, you don't enter your past. You create a new branch, a separate stream of reality. In this view, paradoxes vanish. You can change anything because it's no longer your original timeline. And here, we begin to glimpse the quantum horizon, where particles don't have fixed states, where timelines don't collapse until observed, where possibility branches into multitudes. What if every decision spawns a universe? What if every paradox finds resolution, not in logic, but in multiplicity? And what if you're already living in one of those branches? Not because someone time traveled, but because you did, long ago, or far ahead, leaving ripples you'll never see, a letter you'll never remember writing. Let's go there next, into the branching tree of quantum possibility, where time doesn't just bend, it fractures. What if the universe never makes a choice? What if, at every fork in the road, every coin flip, every particle that could spin left or right, the cosmos refuses to decide and instead says, yes, one version turns left, another right, one survives, one doesn't, one becomes you, and another becomes someone else almost you, but not quite. This isn't science fiction. It's the many worlds interpretation of quantum mechanics, a radical, mind-bending, and increasingly respected way to understand the very fabric of reality. And it might just be the key to solving the biggest riddle in time travel, the paradox. Let's return to that moment, the time traveler saving their younger self, handing them a letter they never wrote. Who created the letter? Where did the idea come from? In a single timeline, it's a loop with no origin, a bootstrap paradox. But what if time isn't a single line? What if it's a multiverse of branching possibilities, where every cause and effect, even the self-contradictory ones, are permitted, as long as they each unfold in their own stream? Now the paradox dissolves, because the older version of you who goes back in time doesn't return to your past. They step into another timeline, one where the letter is received by a different you and everything proceeds slightly, subtly differently. Now the letter has an origin, it came from another world, and the paradox isn't broken, it's distributed. Let's step into the quantum world for a moment, the realm of uncertainty, probability, and infinite potential. In classical physics, everything is clear. A planet is either here or there. A ball either rolls left or right, cause leads to effect in a chain you can trace. But in quantum mechanics, particles don't exist in a single place until you observe them. Until then, they live in a superposition, a cloud of possibilities. They are everywhere and nowhere, alive and dead, here and not. Think of Schrödinger's cat, the famous thought experiment. A cat in a box with a vial of poison that's released depending on a quantum event. Until the box is opened, the cat is both alive and dead. Two realities, one mystery. But the many worlds interpretation, first proposed by Hugh Everett III, takes this further. It says the universe doesn't choose between outcomes. It splits. In one world, the cat dies. In another, it lives, and both are real. The observer doesn't collapse the wave of probability, they simply join one of its branches. So, what does this have to do with time travel? Everything. Because if quantum mechanics allows multiple futures, it may also allow multiple pasts. You step into a time machine. You go back, but not into your past. Into a past one of countless variations branching out from your original history. You meet your grandfather as a child. You change something. Maybe you prevent a marriage. Maybe you cause one. In your original timeline, your actions never occurred. But in this new branch, you've changed the course of everything. And the paradox, the contradiction, never arises. Because the you that goes back in time was born in a different world. And the timeline you enter is not your own. This is called the multiverse resolution of the grandfather paradox. In your world, you exist. In the new one, your grandfather may not have children, but it doesn't cancel you because you came from a different branch entirely. Now extend this idea further. Not just one decision, but every decision. Not just one paradox, but every potential resolution. A tree of timelines, infinite, ever-branching. One where you became a scientist, one where you became a soldier, one where you never existed. One where you created the time machine, one where you were saved by the future, and another where you never were. Every quantum event, every flicker of possibility births a new universe, and time travel becomes navigation across these branches, not bending a single timeline, but jumping between streams. Physicist Bryce DeWitt, who popularized the many worlds concept, once said, "Every quantum transition taking place in every star, in every galaxy, in every remote corner of the universe, is splitting our local world on Earth into myriad copies of itself." It's not just decisions that branch, it's reality itself, everywhere, everywhen. But this raises a new, haunting question. If there are infinite versions of you, which one is you? The one who dies? The one who survives? The one who goes back? Or the one who stays? In the famous Quantum Immortality thought experiment, a person faces a quantum-based death machine, a device that kills them if a certain particle flips one way, and lets them live if it flips the other. Statistically, they should die. But from the survivor's perspective, they never do. They wake up, again and again, in the only branches where they live. It's a disturbing kind of immortality. A universe filled with ghosts you'll never meet. A hall of mirrors, where death is always happening, but never to you. Now bring that back to time travel. Imagine stepping into a wormhole, not to revisit your childhood, but to watch it happening slightly differently. A new you, reading a different book, loving a different person, making a different choice. And it all exists, because the universe refuses to collapse. It splits. This doesn't just solve the paradox. It rewrites the meaning of time itself. There is no single past. There is no fixed future. There are only paths, and your consciousness rides just one of them at a time. Time becomes a forest, and your awareness is a thread, weaving through it. But what if you could jump threads? What if the time machine doesn't send you backward, but sideways? To the version of reality where you didn't lose her, where you said yes, where the letter was never burned, where you never stopped believing in the impossible. This is the true promise of quantum time travel, not to change your past, but to choose your present again and again, to dive into the multiverse and find the life you lost, or the one you were too afraid to reach for, and maybe to forgive the one you have. Let's go deeper, because even this infinite forest may not be the end. There are stranger possibilities waiting, stranger than death, stranger than paradox, stranger than multiverses. Let's step into the final corridors of time, where logic fades and only existence remains. If every version of you exists, if every choice spawns a branch, then who or what are you? Not the flesh and breath, not the name on your passport, but the you who sees, remembers, endures. The self who awakens each day inside a single timeline, while countless others echo outward, ghost-like, just beyond reach. This is the fractal self, a consciousness branching with the universe, a single thread looping endlessly through possibility. And nowhere is this more disturbingly explored than in the concept of quantum immortality. Imagine this: you're strapped to a chair. Before you, a robotic arm hovers over a fragile vial of lethal gas. Connected to the arm is a quantum sensor, a device designed to measure a subatomic particle that has a 50/50 chance of flipping to state A or state B. If it flips to A, nothing happens. If it flips to B, the hammer falls. Your odds of surviving one trial are 50%, 2 trials, 25%, 10, less than 1 in 1,000, 100, 1 in 1,000,000 trillion, and yet, in the many worlds, you survive. Not everywhere, but somewhere. In one branch, the hammer never falls. The particle flips to A again and again and again, in defiance of statistics, in defiance of death. And as the others die, their world lines ending, snuffed out, one path remains. You, alive, always. You walk out of the chamber, not because you're lucky, but because, in the infinite branching of the multiverse, there must be a version of you who survives every trial. This is quantum immortality, a horrifying, beautiful idea, that you, the experiencing self, can never die, because your consciousness will always continue in the branches where it survives. No matter how unlikely, no matter how narrow, you are the survivor, always waking into the version where you still exist. But this idea isn't comforting, it's haunting. Because what if you survive? Not because you're safe, but because you're trapped? What if the you that keeps waking up must face darker and darker timelines? Increasingly improbable situations where you linger alone, wounded, broken, lost, long after all sane versions of reality have ended? You become a refugee of chance, drifting through a narrowing funnel of quantum branches, kept alive not by hope, but by mathematical inevitability. You are the ultimate time traveler, moving forward not through space, but through possibility itself. And in this terrifying truth, something even stranger emerges. The idea that your identity is not fixed, that you are not one person, but all of them. Every branch of the multiverse contains a version of you. Some are close, others are unrecognizable. A childless you, a cruel you, a heroic you, a you who never watched this documentary, a you who built a time machine and broke the laws of nature, and all of them are you. Together, they form a fractal, a self-similar pattern stretching across reality. Each branch, a variation. Each world line, a vein of the same consciousness. You are not a point, you are a pattern. You are not a body, you are a possibility field. And as these versions splinter, shift, and sometimes collide, we begin to see something truly alien. The loop of identity, the idea that time travel doesn't just let you revisit your past, it lets you revisit yourself. Not metaphorically, literally. You may meet your younger self, guide them, save them, or betray them, and in doing so, become the very reason you exist. A bootstrap paradox of the soul. Who raised you? Who inspired you to study science? Who handed you the envelope? It was you, or a version of you, from another stream, another fork, another echo of the same original flame. And if all versions of you exist simultaneously, if the multiverse is infinite, and your identity is fractal, then time travel isn't a machine, it's a mirror. You stare into your past not to change it, but to understand what you already are. And in that understanding, you meet the most terrifying paradox of all. There is no original you, no prime copy, no true timeline, only reflections, only branches, only the loop of becoming, replaying, refracting, and evolving with each quantum breath. You are not a story. You are a library, an archive of selves, and in some branches you live forever. In others, you die young. In some, you never existed at all. And the version watching this, you are the survivor, the branch that led here, not because of fate, but because somewhere in the branching maze of reality, you were always going to arrive at this moment. To hear this, to wonder, to remember. But now you must ask, if you can survive anything, if there is no one, you, then what is choice? What is morality? What is love, loyalty, betrayal if every version of you plays out somewhere? Are we free? Or are we merely exploring every version of freedom? This is the real question at the end of time travel. Not can we escape time, but can we escape ourselves? And what happens when the loops close? Not in space-time, but in identity, where you are your own cause, your own ghost, your own God. Let's step into the final echo, into the great recursion, where everything has already happened, and everything is still unfolding. What happens when the journey ends? Not the journey through space, or even through time, but through you. You've traveled across paradoxes, through wormholes, multiverses, and branching identities. You've faced death, met your future, and glimpsed infinite versions of yourself living out lives you'll never remember. But now, we arrive at the final horizon, the last paradox. Not of physics, not of time travel, but of consciousness. Because if time isn't linear, if cause and effect break down at the quantum level, if identity loops upon itself, and reality splits with every decision, then what makes this moment feel real? Why does now feel like the center of everything? Why does this particular version of you feel like the only one that matters when trillions of others exist in the same breath? And here's the deeper mystery. What if even time is not fundamental? What if time, like color or sound, is a construction, something your mind assembles from the flow of change? Your heartbeat, the tick of a clock, the decay of a memory. Einstein once said, "The distinction between past, present, and future is only a stubbornly persistent illusion, and yet it hurts to lose someone. It matters when a moment ends. It feels like time is real. So what's the truth? Physics tells us that the laws of the universe are time-symmetric. The equations work just as well forward as backward. The arrow of time, the direction from past to future, is not written into the laws themselves. It's emergent, a consequence of entropy, the tendency of systems to move from order to disorder. You remember the past, not the future, because there's more information behind you, more patterns that have decayed, more order that has unraveled. Time flows because memory does. Your brain is a machine that records what was and predicts what could be. It stitches them together into a story. That story feels like you yourself moving through time. But what if that's the illusion? What if consciousness isn't traveling through time at all? What if consciousness is timeless? A spotlight, a window, an awareness looking through a body, through a story, through a universe. In this view, all moments exist simultaneously like pages in a book, past, present, and future already written. But you, the reader, can only see one page at a time. You are the one who turns the page, not your brain, not your biology, you, the awareness beneath it. This is the final paradox, that what we call time travel may not be about moving through space or shifting events, but about shifting awareness. You don't need a time machine, because the self is already non-local, already unbound, already watching from a place outside of time. Have you ever caught it? That flicker, that dreamlike moment where you feel like you've done this before, déjà vu? Or waking from a dream that felt more real than life? Moments where the page turns too fast, where the illusion of linearity stutters. What if these aren't accidents? What if they're glimpses, cracks in the shell of reality, revealing that the observer has no true origin in time? What if the thing watching through your eyes has always existed, not born, not aging, just watching? Physicist Julian Barber argues that time doesn't flow at all, that the universe is composed of countless nows, frozen configurations of everything that exists. Our sense of movement, of continuity, is just the comparison between these frames. Like a film strip, each still image is motionless, but played in sequence, they produce the illusion of life. So what, then, is the projector? What is the awareness that watches? Could it be that consciousness is not inside the universe, but the universe is inside consciousness? This is the place where physics hands the torch to philosophy, where mathematics stares into the abyss, and the abyss speaks back in metaphor. Perhaps the Big Bang didn't create time. Perhaps it was simply the first page your awareness turned to. And perhaps death isn't the end of the story, just the end of this storyline. Your awareness flips to another timeline, another body, another version of you in another now, like light refracting through a prism, always the same source, always different colors, and so the traveler awakens, not in the past, not in the future, but in the present, again and again and again, each moment a portal, each breath a choice, each thought a universe being born. You are the time machine. Your choices are the coordinates. Your awareness is the eternal traveler. And maybe, just maybe, that's the secret. Time travel doesn't grant you power over history. It grants you power over perspective. And in that shift, in that quiet awareness, you realize you were never moving through time. Time was moving through you. So what is time travel? A wormhole? A paradox? A machine? Or a metaphor for something deeper? The longing to return, the desire to change, the courage to understand. And maybe, just maybe, it's not about breaking the laws of physics, but about remembering that you were never bound by them to begin with. So ask yourself, where will you go next? Because the machine is already running, and the next universe, is just a thought away.